first presenter will be Alan. You want to come in?
My name is Alan Grosvenor, and I have a company called MSBAI. We automate a variety of digital engineering and operations workflows, and we can start running this. The last one. That's an animation. Like if you want to just, I don't know if it's possible to cycle it. Anyway, this is this is an example of synthesizing a broad range of aerial vehicles, geometries in a digital engineering process. And the way we've done that is we've taken Microsoft's 2 billion parameter trellis model, and we've trained it with a hybrid training approach. We have used a series of publicly available aerial vehicle geometries, plus a very large set of images that we combed off the internet of aerial vehicles, plus synthetic geometries that we autonomously generated by driving a software package that's called OpenVSP. And this methodology enabled us to map from vehicle descriptions to valid geometries. And in the next video that we're going to show, we're showing autonomous setup of building computational meshes, setting up flow solutions, converging them, and running flow solver solution adaptive mesh refinement. And this is all done autonomously. We're autonomously running MeshLab, GMesh, Refine, Salome, SU2, and Paraview in these workflows. And so what you're actually seeing there is an evolution of flow solutions as they're converging and adapting. The reason I got into this is because I started as a user here back in 2009 when I worked at a company called Ramjet Power Systems. We used Jaguar and then Titan to invent a brand new type of turbo machinery that could operate at supersonic speeds like Mach 2, Mach 3. There were no design rules for that, and we had to run monumentally massive numbers of design iterations and guided simulations and optimization processes in order to find something that would work. And then we actually built it and tested it, and our measurements matched our predictions. I went and worked in another company called Maston Space Systems, and we had DARPA's reusable space plane program. I did something very similar on HPCMP supercomputers, but for a reusable boost vehicle. We again built the prototype after the fact, and the measurements matched the predictions. And if we go to the next example here, okay, we just have the 2 videos. We don't have the other ones anymore. I guess that's fine. Anyway, so that's totally cool. So very long story short, there's a lot of reasons why this kind of workflow can go wrong, and you'll have all sorts of errors introduced into your process that ruins your ability to do design. You need full autonomy, intelligent autonomy across the entire spectrum of operations. And we do a massive amount of, we're running every artificial intelligence framework, essentially. We built a multi-framework automated machine learning system, doing a lot of multi-objective optimization, but also we use joint embedding predictive architectures a lot. It's a methodology that came out after transformers, after large language models, that enables to essentially affect a level of compression into the vector space and avoid a lot of noise in the baseline data set and train to the signal a lot better than you otherwise might. And it gives us a lot more quality assurance and a lot of time series operations behavior capability. And I just wanted to say that this is an example of an end-to-end user interactive case of using what we call our Guru system to generate these vehicle geometries and set up the simulations and execute them. We actually demonstrated this live recently across 3 different facilities. Guru was taking the user requests that he was actually speaking at the time, and then executed it simultaneously across HPCMP's Radar supercomputer, Argonne National Laboratories, Aurora supercomputer, and Frontier here. And it's set up so that whichever one runs in the queue first, that's the one that picks up, and then it just cancels the other jobs. We've done a lot for multi-facility. We built an API, a proxy API layer with authentication that the user does once, and we then launch an API service on the local system. The facility side connects back through a secure tunnel. We build container libraries of the environments software we compiled for them, specifics for the individual schedulers on the local systems and the local hardware. And we do unified job monitoring so that you can submit to multiple queues and readily add additional facilities. So that's what we've done. The next video that we show is just kind of like a fun looking example of a visualizer that we put together of some of the results. We tend to run thousands of these kinds of models, and generally we're running them in a non-interactive mode. When you're running 1,000 operational conditions and targeting and design, you don't want to do it interactively, but you want to look at the results at the end. Thank you very much.
Thank you. Woo!